Welcome back. I hope your semester is going well thus far. In this video, I'm going to show you how to conduct a z-test in Excel. To conduct a z-test, you need to have sample data that you want to compare to a known population. So what I mean by known population is that you need to have a population mean and a population standard deviation. So if you don't have those two things, then you can't do a z-test. If you only have a population mean, then you have to do a single sample t-test, which we'll learn about in a later video. As always, make sure you open up the Excel directions as well as the Excel spreadsheet below. So let's start with the spreadsheet. You'll notice here we have two columns of information. One is the participant ID numbers, and then the second column is the variable that we'll be working with. In this case, it is siblings. If you go down to the code book, you'll get a description of that variable. In this particular case, it looks like it's how many brothers and sisters, including step siblings, do you have in your immediate family? And so this was a question that was asked of all of you at the beginning of the semester. I combined your data with the data from last semester. All right, and so before we get into this, we need to know a little bit of a context of why we're doing this analysis in Excel. And so there is a scenario here in the code book section. When it comes to a regular assignment, you'll have it in the Qualtrics link, but here I just put it in the spreadsheet just to make it convenient for us today. So our scenario here is suppose research has shown that there are more siblings in Southern families than in families in the overall U.S. population. So that sentence tells us something. That sentence tells us that there has been previous research and that research has found something. In this case, that Southern families tend to have more siblings. If that's the case, then we can do what's called a one-tailed test. And you can go back to the narrated PowerPoints to talk about when you have a one or a two-tailed test. It looks like in this case we have a one-tailed test. We have a pretty good idea of what to expect given the data that we have. All right, so we would like to verify if this finding holds true for Alabama families. And again, Alabama is in the South, so we would expect Alabama families to have more siblings than the overall population. So the number of siblings in a typical family in the United States is 0.87 with a standard deviation of 1.38. And that comes from US Census data. So we sample students from our statistics class, just like I mentioned, came from this semester and a previous semester. We ask them about their brothers and sisters. And we come up with this data set that has all the numbers for our particular variable. Now for this particular example, we're going to use an alpha of 0.01. So that alpha is an error rate. In this case, it's a type 1 error. So the type 1 error tells us if we conclude at the end of the study that indeed Alabama families have more siblings than the overall U.S. population, there is a 1% chance that we could be wrong. And that's what that 0.01 represents. It's a probability. If I turn that into a percent, I would multiply that probability by 0.01, and that would give me a 1% chance that my conclusion, if I reject the null hypothesis, if I say Alabama families have more siblings than the overall U.S. population, there's a 1% chance that I would be wrong. And that's what that alpha, that type 1 error rate is telling us. And that's going to be important because that's one of the fields that we're going to need to fill in as we do our Excel work here today. So with that said, let's take a look at our Excel directions. You're going to notice that there's going to be several steps here. We'll go through the hypothesis test. We'll also get an effect size as well as a confidence interval. So the very first thing that we want to do is before we do anything as far as any data manipulations, we want to go ahead and get our descriptive statistics for the sample. We want to do that first because we're going to manipulate the data. We're actually going to end up doubling the data set, and we don't want to get descriptive statistics on the double data set. The only reason we're going to double the data set here is to fool Excel. There is no single sample z-test in Excel, and so we have to trick Excel a little bit to get the numbers that we want. And so we want to start off with getting those descriptive statistics. Now you know how to get descriptive statistics. You've been doing it all semester. I'm just going to go to the data collection tab down here, and I'm going to go up here to data analysis. You know the drill at this point. I'll highlight my column for siblings. Because I am highlighting that column, I have a label in the very first row. So I want to check that labels in the first row box. I also want to check my summary statistics box. And then I'm going to put my output someplace a little bit away from my data, because I'm going to need at least one column before I can conduct my analysis. All right, so I'll just put it here in cell F2 and click OK. And that's going to give us some of the information that we're going to need. It's going to give us the sample mean. That's going to be really important. It'll give us some other data as well that we'll need to report, but won't be as important. So you notice we'll have a sample standard deviation. That's not going to be too useful to us, but when we do describe our sample, we do want to include that if we were doing a write-up. Another thing that we're going to see down here is a count. We will need that count later, so you may want to mark that as well. Okay, so let's go back to our directions. We've got our descriptive statistics. Now we need to prepare the data in order to do a z-test in Excel. All right, so like I mentioned earlier, Excel only has a z-test for 2 samples. We don't have a single sample z-test in Excel, so we need to trick Excel a little bit here. So to do that, the first thing we're going to do is we're going to push all our empty cells down to the bottom. Now, I don't think we have any empty cells here, but just to be cautious, I'll go through the steps anyway. I'm just going to highlight that column. I'm going to go to Sort and Filter and Smallest to Largest. I'll click Sort. I'm just going to scroll down to the bottom here. And yeah, we don't have any empty cells. But if we did have empty cells, we want to make sure that we deleted any of the participant ID numbers for those empty cells. Here we don't have any, so we don't need to worry about that. The next thing we're going to do is we're going to double the data set, and we're going to do that by copying data, and just the data, not the label, copying the data and placing it below the original data. So in my spreadsheet, I'm just going to highlight, so I'll left click and hold. I'm just going to get the numbers. Notice I'm not going to get the title here. I'm not going to get the label. I'm just going to get the numbers. And I'm going to copy it. And there's 2 ways I can do this. I can right click and click on copy. Or if you know the shortcut, you can hold down Control and press C, and that'll copy the data as well. All right, so I'm just going to go right below my data here. I'm going to click on the cell. I'm going to right click, and I'm going to paste. In this case, you notice there's several different paste options. I'm going to paste as values, and that's that clipboard that has the numbers there. The other way you can do that is you can hold down Control and then press V, and that'll paste your values as well. So Control V will also paste. But notice what we've done. We've doubled the data set. Now that doesn't mean we now have 202 observations in our sample. We still only have 101 observations in our sample. We only doubled it to full Excel so we can get our results for a single sample z-test. So once I've doubled the data set, I then need to create a second column for just the population mean. All right, we want to match that to the number of observations that are in our doubled data set. So what I'm going to do is I'm going to put a label here. I'm just going to put population mean or pop mean. And then I'm going to go to the scenario, and I'm going to put in that population mean. So remember, we're going to compare whatever our sample mean is to the population mean for the United States. So the sample represents a population of families in Alabama. I want to compare that to the population data in the United States. So it looks like my mean is 0.87. So I'm going to type in 0.87. I'm going to drag that value down so that I have 0.87 next to every single one of my observations in that doubled data set. So again, all I did to drag that down was click on the cell, hover over that bottom right-hand corner where that box is, left click, and then drag it down. Just like we've done in previous videos. So now our data is prepared and ready to go to conduct a z-test. The next thing I need to do is I need to go to my data analysis Toolpak, and I need to select the z-test to sample for means, and I'll click OK. That's going to open up a dialog box where I'm going to place in some information. I'll walk through that once I have that dialog box open. Let's go back to the Excel spreadsheet, go up to Data, Data Analysis. I'm going to scroll down to my list, and you're going to see some tests down here. We have some t-tests, and then at the very bottom, we have a z-test to sample for means. That's the one that you want. So click OK, and you're going to notice that we have 2 variable ranges. That's going to be for our 2 columns. So the first variable range, I'm going to click on column B here for siblings. And then for my variable 2 range, I'm going to click on column C, which is that population mean. You're then going to notice this next box that says hypothesized mean difference. So what that is indicating is what would you expect to happen based on the null hypothesis. And so the null hypothesis here would be that there would be no difference. Now that's not the one that we would write out, but that's just the general null hypothesis that if the mean of the sample was exactly the same as the mean of the population and I subtracted them, I would get 0. So I'm going to put 0 in that particular box. Now remember, when it comes to writing out your null and research hypothesis, you want that to match whether you have a 1 or a 2-tailed test. So here we have a 1-tailed test. The null hypothesis would be that Alabama families have fewer siblings or the same number of siblings as the overall US population. We're not writing it out here. All we're doing is we're putting in a value. That value is going to represent 0. If the means were the same, then the difference would be 0. And in most cases, that will be what you would type in that particular box. At least that's what it'll be in this class. If you take a more advanced class, you can put other values in there and test to get other values other than 0. Next, you're going to see 2 boxes here for variance, and it says it's the known variance. And so we don't have the known variance, and certainly you don't want to use the variance that's in your output here because that's the sample variance. That's based on our sample. It's not what's known in the population. When we see variance known, we're talking about the population variance. Even though we don't have it currently, we can calculate it from that population standard deviation that was given to us in the scenario. And so if you remember, that standard deviation was 1.38 siblings. And so that's the value that we want to use here. And so the relationship between variance and standard deviation is that the standard deviation is the square root of the variance. So if it's the square root of the variance and I have the standard deviation, then all I need to do is square the standard deviation and that will give me the known variance. So I'm going to open up a calculator here. We're going to type in 1.38. I'm just going to multiply it by itself to square it. And then that's going to be the variance that I put in to Excel. So I'm going to put 1.90. I'm going to put that in both of those boxes. So known variance for variable 1, variable 2, we're going to put the same here because it's a single sample z-test. We're going to put 1.9. But just remember that that value has to come from your scenario, has to come from your known standard deviation. You take that value, you square it, and that's going to give you the known or the population variance. All right, so remember we did select our columns B and C. We have labels in that very first row, so we want to check that labels box. Notice here we're then given a box for the alpha. The alpha default is 0.05. That's the most common alpha for research in the human sciences. Now you remember from that scenario, we said the alpha was 0.01. So I'm going to change that to an alpha of 0.01. And then finally, we have to put our output someplace. So in this case, I'm going to put my output someplace on my spreadsheet. I'll probably put it just right below my descriptives. Just make sure you check inside the box there when you do that, and then select your cell. So I'm just going to put it here in F18, right below my descriptives, and then I'm going to click OK. And that's it. So there's our results for the z-test. Just scroll down and take a look at it. You're going to notice a few things in these results. You're going to notice that it's going to give you the mean of the sample as well as the mean of the population that you entered in for that second variable. So the mean of 0.87 all the way down is going to be 0.87. It's going to give you that known variance that you typed in. Again, that's just the standard deviation squared from the scenario. Note here that it says your observations are 202. Do not use that. The only reason it says 202 is because we double the data set to artificially get the results for a single sample z-test. Our count is still actually 101. And so if you're asked to report the number of observations, that is the value you're going to use. It's 101. After that, you're going to see that we have a z value. That is your z statistic. So even though it doesn't say zstat, it is your Z statistic. In this case, it's a Z statistic of 6.65. That's a rather large Z statistic. Anything above 3 is a value that we would consider to be rare. It wouldn't happen very often. So in this case, we're probably going to reject our null hypothesis here. All right, so we have that Z statistic. We need to compare it to something. We want to compare it to our critical value. So remember, we have critical values for 1-tailed tests and 2-tailed tests. Remember, in this particular scenario, we said we expect that the number of siblings in Alabama families is going to be higher than the overall US population. That's a 1-tailed test. And so the critical value we want to compare to is this value right here. Now remember that in Excel, that this value will always be positive. You need to know when it's negative. And so if our scenario had read that research had shown that Alabama families have fewer siblings, then when we report this value, we would need to indicate that it's a negative 2.33. In our particular situation here, we expect Alabama families to have more siblings in the US. We're going to leave that as a positive value. But just remember that in the output, it's not going to indicate when it's negative or when it's positive. It'll always give you the positive value. The reason for that is if this value is supposed to be negative, it's negative because of a conceptual reason, not a mathematical reason. So you need to know conceptually when this value is positive and when it is negative. In this case, it's positive. So I'm going to quickly just draw out the normal distribution. And I'm going to put on this distribution where the critical region is. So remember, the Z distribution is centered at 0. Remember that this is a distribution of means, not a distribution of scores. We're using averages, in this case, over 101 participants. And so we mentioned before that we expect, in this case, that the number of siblings will be higher in Alabama than in the overall US population. That means we're going to set our critical region in the positive direction here. We expect our mean to be higher. So our critical region would be right about here. And remember that this represents 1% of the population. That says population there. And so we're going to set that point where that critical region starts at the critical value. In this case, of a Z critical equals 2.33. So that means anything beyond 2.33 is going to fall in our critical region, and that's where we're going to reject the null hypothesis. Any value that is less than 2.33, so anywhere in this range, we're going to fail to reject the null. So if I'm looking at my Z statistic, I got 6.65. That does fall out over here someplace, 6.65, in this region where I would reject the null hypothesis. So if I reject the null, I'm rejecting that there is no difference where Alabama families have fewer siblings than the overall US population. I'm rejecting that. It appears that based on our sample, based on our statistics, that Alabama families have more siblings than the overall US population. And that would be our statistical decision. Now, the statistical decision is always at the group level. So what if we wanted to know for the individual family level? What does this mean for an individual Alabama family? So we know collectively as a group, it appears that Alabama families have more siblings. Could we expect the same on average for an individual family? In order to answer that question, we have to conduct what's called an effect size. So let's go ahead and go back to our directions page. Notice we already completed this step here, step 3. Let's go down here to step 4. You're going to notice that this is where we're going to get additional analyses. We're going to get that effect size, and then we're going to get that confidence interval. So the effect size is what's going to tell us the impact of our research at the individual level rather than the group level. And we know that based on the formula. So the effect size formula is the mean of the sample, that's M. So remember, the letters that you're used to represent sample data. So M here is the sample, mean for the sample, minus mu. And mu is a Greek letter, so it represents the population. We're going to take the mean of the sample minus the mean of the population. Then we're going to divide by the standard deviation. And so the standard deviation is on a distribution of scores. So a distribution of scores is a distribution of individual values. So if you're looking at that formula and you look at the z-test formula, you're going to notice that they're very similar. The z-test formula is z equals the mean of the sample minus the mean of the population on a distribution of means divided by, not the standard deviation, but the standard error. And so if you remember, the standard error from the narrated PowerPoints is simply just the standard deviation in the population divided by the square root of the sample size. So what that does is that takes our data and accounts for the fact that we have multiple observations. In other words, we have a group, in this case, a group of 101 participants. But we don't want that here when we get the effect size, because we don't want to get a result at the group level. We want to get it at the individual level. What's the individual impact? So just notice that the formulas are very similar. The difference is in that denominator. For a z-test or a z-statistic, we're dividing by the standard error, which is the variation on a distribution of means. Whereas with an effect size, we're dividing by the standard deviation, which is the variation on a distribution of scores. And make sure you know the difference between distributions of scores and distributions of means. So let's get this effect size. So we'll have to do this in Excel. So I'm just going to go below my z-test output. I'm just going to type in effect size. Then I'm going to go in over to the next cell, and I'm going to put it in my formula there. And so remember that our formula is going to be the mean of the sample, which I have in my output already, minus the mean of the population, which is also in the output. I'm just going to click on those two cells. We're going to close parentheses, and now we're going to divide by the standard deviation. Now remember here, this is the population standard deviation. It is not the standard deviation that is in your output up here. This is the sample standard deviation. Don't use that. What you want to use is the population standard deviation, which in our scenario was 1.38. All right, and then we hit enter, and that's going to be our effect size. In this case, it's 0.66. So just to quickly remind you, if we go to that code book, right, we're going to see that standard deviation in the population is 1.38, and that's where we got that value for a formula. All right, so 0.66, so what does that tell us? Well, that tells us that we can expect that any individual Alabama family is going to have 0.66 standard deviations more siblings in their household than what we would expect in an individual family in the United States. In this particular case, 0.66 would be a large effect. This would be a good time to review our effect size conventions. So remember, an effect size of 0 is no effect. An effect size of around plus or minus 0.2 is a small effect. Effect size of plus or minus 0.5 is a medium or moderate effect. And an effect size that's around plus or minus 0.8 equals a large effect. And so it's not cut off, so it's whichever one is closest to. So in this case, 0.66 is going to be closer to a large effect, not by much, but closer to a large effect than it would be to a small or medium effect. So it looks like in this particular study that when it comes to Alabama families, not only do we find a difference at the group level, that Alabama families have more siblings in them, we also find it at the individual family level, that on average we'd expect that any individual family would have more siblings than the overall US population. And so when it comes to research in the behavioral sciences, if we have a medium or moderate to large effect, we're going to say that there's some impact on the individual level. If our effect size is small or there's no effect, then we're going to say that there is no impact at the individual level. And so realize that you can reject the null and find that there's impact at the group level, but find out for the individual level, there's no effect. So we would say there's no practical effect in that case. or vice versa. We may fail to reject the null, but find a large impact for the individual or at the individual level. And so understanding what each of those represents is important. Here, they're both saying the same thing at the group and individual level. It looks like Alabama families have more siblings than the overall US population. So we have one more thing to do. We need to get our confidence intervals. And so the reason why we want to get a confidence interval is because we want to get a range of where we would expect the true population mean to fall. So again, we want to know about Alabama families, but we haven't measured all of the Alabama families. We've only measured those in our sample. And so the sample becomes our best guess of what the population mean is for Alabama. But we know that the sample mean is not going to be exactly what the population mean is. And so we need to create a range of where we would expect the population mean to fall. And that's what that confidence interval gives you. It gives you a range of where we expect the population mean to be. So to do this, we need to get a standard error. So that's not in our output. We need to calculate that standard error. And then we need to take our two-tailed critical values. And again, we're going to use two-tailed critical values here, regardless if we have a one or a two-tailed hypothesis test. So whether we have a one or two-tailed hypothesis test doesn't matter to confidence intervals. Confidence intervals will always, always, always be two-tailed. So make sure you use the two-tailed critical values. And so what we're going to do is we're going to get a lower bound for the range. We're going to get an upper bound for the range. Get that lower bound, we're going to take the negative z critical value. We'll multiply it by the standard error, which we'll need to calculate. And then we're going to add the mean of the sample. So notice that we're adding the mean of the sample, not the population mean here. To get that upper bound, it's going to be exactly the same thing, except our z critical value is now going to be positive. So let's go to our spreadsheet. The very first thing we need to do is we need to get that standard error. Remember that the standard error formula, so here's our symbol for standard error, is the standard deviation for the population divided by the square root of the sample size. So I'm just going to go to the cell right next to my standard error here, and I'm going to put in that formula. I'm going to hit equals. I'm going to type in the standard deviation for the population. So again, not in your descriptive output, but the standard deviation that is in the scenario. And I'm going to divide by the square root of the number of observations. So you'll be tempted here to use 202 because that's what's in your z-test output. But remember, we doubled the data set to full Excel. That's not the value you want. The value you want here is 101. We're going to divide by 101. And remember, we need the square root. So we're going to take that 101 to the power of 0.5. So we'll take 1.38, divide it by 101 to the power of 0.5, and that'll give us the square root of the sample size. And then just hit enter. And it looks like our standard error in this case is going to be roughly 0.14. Now we need to get the confidence intervals. And so we need a lower bound and an upper bound. By the way, this will be the 99% TI, and it's 99% because remember we have a 1% chance for an error. Alpha was 0.01, so that's a 1% chance for an error. And so we need our lower bound and we need our upper bound. So to get that lower bound, remember we're going to take the negative z critical value. We're going to multiply by that standard error we just calculated, and we're going to add the sample mean. I'm going to hit equals here. I'm going to press the subtraction sign for a negative. I'll click on the two-tailed critical value. In this case, it's 2.57. Now to multiply, you need to press the asterisk key. And then I'm going to multiply it by that standard error we calculated. And you can just click on the cell. And then I'm going to add the sample mean. And so our sample mean is up here in our output. In this case, it's 1.78. And then once I have that, I'm going to hit enter. So remember, it's going to be a negative sign. We're going to click on the two-tailed critical value. We're going to multiply by that standard error, and then we're going to add the sample mean. And so it looks like our lower bound is 1.43 siblings. Let's get our upper bound. It's going to be very similar. It's going to be equals. We're going to take the positive critical value here. So don't put in the negative sign. Just click on the two-tailed critical value. We're again going to multiply by that standard error, and we're going to add the sample mean. So same thing, except we're not going to use the negative critical value here. And we'll hit enter. So just remember that when it comes to the confidence interval, you're always going to use the two-tailed critical value, even if you have a one-tailed hypothesis test. So the confidence interval is different than the hypothesis test. And so they're going to have different rules. So confidence interval is always two-tailed. Your hypothesis test could be one or two-tailed. All right, and so that's going to give us the values of 1.43 and 2.1, looks like 2.14. So if I was to interpret this and write it out, I would say that there is a 99% chance, remember 99% confidence interval, a 99% chance that the population mean for the number of siblings in Alabama families is somewhere between the values of 1.43 and 2.14. So that's it. That's a z-test in Excel. We did the hypothesis test and got the results here. We then did additional analyses. We got an effect size to see what the impact is at the individual level. And then we got a confidence interval to create an estimate of where we expected the true population mean to fall, in this case for Alabama families. So please remember to upload your spreadsheets, again, with your name as the file name and submit it below. Thank you.